Yeah, so I'm going to be talking about event-driven architecture, and if you're not using it already, maybe why you should use it or why you should at least think about it and keep it in mind. So event-driven architecture is a software design pattern that focuses on the flow of events and exchange of information between components within a system. In the system, components communicate through the generation, detection, and handling of events, which are significant occurrences or changes in state. So unlike traditional architectures that follow a request-response model, event-driven architecture promotes loose coupling and scalability by allowing components to react to events asynchronously. This decoupling enables greater flexibility, modularity, and extensibility, making it easier to adapt and expand the system without causing cascading changes throughout the entire architecture. This architecture is particularly well suited for complex and dynamic systems where components need to be responsive to real-time events and handle high throughput scenarios. Okay, now that everyone understands the basic principles of event-driven architecture, let's get into some more detail. Okay, there you go. The architecture is comprised of three components, namely event producers, such as a mobile app, a website, or a point of sale, event brokers, such as an event router or event store, and then finally an event consumer, such as a database or microservice like AWS Lambda. Okay, now why should you be thinking about how to adopt EDA into your applications? Firstly, agility across teams. Modern applications are growing in complexity and can comprise of several cloud-based services, software as a service services, and on-premise services all at once. Development teams working on these services need to be able to work independently and with agility in building and managing and updating new services. This increases the speed of feature development. This is a huge advantage, as we all have been involved in scenarios where changes to one service unintentionally impacted other services in the application. And in these architectures, because these services were so tightly coupled and component scalability impacted the entire system, meaning failure in one system created failures in another. Secondly, event-driven services are resilient and reliable, as well as being able to scale up and down depending on the demand. Services can fail independently of each other, removing a single point of failure. Thirdly, and related to the previous point, customers expect our applications to be responsive and are not willing to accept having to wait for what they want. EDA helps with this because services are responding to an event. Delays or failures do not impact how or if other services respond. Lastly, and most importantly, in most of our clients' eyes, is cost efficiency. Event-driven architecture allows you to only pay for what you need when you need it. This can potentially lower the cost of your applications. Potentially is the key word in this sentence. Now that everyone agrees that EDA is the best thing ever, let's see some of its most common use cases. Firstly, microservices communication for web and mobile backend. This use case is often seen in retail or media and entertainment websites. These websites often experience unpredictable traffic. Take an e-commerce website, for example. The flow goes something like this. A customer places an order, the order is sent to an event router, and all downstream microservices can pick up the order for event processing. These downstream services would be submitting the order, authorizing payment, and sending details to shipping providers. Because each microservice can scale and fail independently, with event-driven architecture, there is no single point of failure. As an example of why scaling is so important for retail services, the traffic will be much higher on payday, and even higher than that on Black Friday, for example. The same goes for media or entertainment websites, where traffic will typically be much higher in the evening. Second use case is automating business workflows. This use case can be seen in financial services transactions or business process automation. For example, when a customer creates a new account application with a bank, the bank will have many steps, including data checks and even human approval stages. The stages can be handled with a workflow service, with workflow automatically triggered anytime a new account application is submitted. Another use case is infrastructure automation. Teams running compute-intensive workloads such as financial modeling, AI, and machine learning, computational fluid dynamics, or even weather forecasting and genomics. This is extremely important. These tasks can trigger compute resources to scale up for highly parallel processing and then scale back down once they're finished, meaning that you don't have to pay the entire time, only when you're using. Another example could be in a highly regulated industries where you could spin up security postures in response to an incident or take remediation action when a security policy sends an alert. Okay, now moving on to how stream processing fits into event-driven architecture. So Riot Games are developers of online games such as League of Legends. They ingest, on average, 20 terabytes of data a day. This data is used for a range of services, including matchmaking, security, in-game personalization. And if you have ever played League of Legends, you'll know that most importantly, player behavior and game balancing. So what is stream processing and how does Riot use it to help process their data? Stream processing complements and enhances event-driven architecture. In EDA, events trigger actions within a system. Stream processing takes this concept to the next level by enabling real-time processing and analysis of data of event streams as they occur. As events are generated and flow through the system, stream processing platforms efficiently capture, process, and react to them instantly. This enables immediate responses, leading to faster decision-making and improved system responsiveness. Stream processing allows for event aggregation, filtering, and transformation, helping to manage Riot's daily 20 terabytes of data efficiently. With Riot's old system, data received from players was only available for querying 6 hours after it was produced. Applying event-driven principles and stream processing with Amazon MSK, a stream processing service, they were able to reduce this time from 6 hours down to only 5 minutes. This obviously affected them quite drastically. Okay, and then my last point is it wouldn't be fair to only talk about the positives and why you should think about it, but include some of the drawbacks of event-driven architecture. I'll briefly mention some of them now. First of all, complexity. Event-driven architecture can introduce additional complexity, especially in large systems with many events and event handlers. Managing event flow, sequencing, and consistency can become quite challenging at times. Secondly, event ordering. Ensuring the correct order of events can be difficult, especially in distributed systems. Some events may need to be processed in a specific sequence, which can complicate the implementation. Thirdly, event duplication. Events may be duplicated, leading to potential data inconsistencies or redundant processing. Handling event duplication can add complexity to the system. And the next is debugging and testing. Debugging event-driven systems can be more challenging than traditional request-response systems. Testing the interaction between events and handlers may require specialized testing strategies. The same is true for monitoring. Slightly more difficult to monitor, and you might need specialized tooling and expertise. And then lastly is error handling. Handling errors and failures in event-driven systems can be complex, especially when considering the potential for cascading failures. And that is my talk.